Welcome to the final session this afternoon. This is the parallelism session. And the talks are going to be presented sequentially. The first speaker this afternoon is Foltzer from Hungarian University, and he's going to be talking about a meta-scheduler for the power moment.
All right, thank you, Simon. Thank you for being here. So this morning we heard a lot about these heterogeneous parallel architectures. So we've got our CPUs, our programmable GPUs, even more exotic things. We have cloud that's part of everyone's startup venture capital proposal. We're going to be in the cloud of some sort. And even things like FPGAs, programmable logic that we can reprogram on the fly. And we want to be able to use all of these if we're lucky enough to have them available to us. So we want to take a picture like this. We have a program for the CPU, the GPU, and for distributed architectures, and combine it into a single program. But it's hard to do this in a way that things just don't go horribly wrong. So in Haskell, we have a bunch of good individual stories. We have, among other libraries, the par monad, which is a deterministic task parallelism model. Uses write-once synchronization variables, lightweight continuation-based concurrency, and it comes out of the box with a high-performance random work stealing scheduler. It's got this nice pure interface, so you write a par computation for type A, you get back type A in the middle of your program. For GPU programming, we have Accelerate, a fine embedded domain-specific language, with all the high-order functions that we as functional programmers use and love every day. Our maps, folds, reduces, and so on. We can run these Accelerate computations in, just like the par monad, the middle of a pure computation, get back our pure result. For the distributed scene, we've got a lot of activity lately around Cloud Haskell, which is an Erlang-style message passing implemented as a library in Haskell. No changes to the runtime system are needed. We have remote procedure calls that just need a little bit of template Haskell, but then we can send messages across the wire run functions. Everything's nice. It's got an issue with composability. Unlike with the pure interfaces, we're sort of committed to this top-level process monad. So it can be a bit hard to mix and match Cloud Haskell. So the problems that arise when you're trying to put this picture together are contention for resources. So if I'm running an SMP scheduler that spawns one thread per core, it'll spawn 4 cores on my laptop. And then I'll spawn the same number of cores when I ask Cloud Haskell to do a bunch of parallelism. So that's not actually speeding me up at all, that's just taking up space. If we want to schedule the same task across potentially all of these, then we run into a problem with that too, because it's not exactly obvious how to decide what runs where. And in the case of GPUs, we have blocking system calls that, if made in the middle of a computation, can completely derail a par monad worker and keep it from doing useful CPU work while the GPU is off doing something. So our thesis is that work stealing provides a good foundation for building the kinds of modular schedulers we need to address all of these heterogeneous resources. And so I'm going to show you how we did that. So work stealing is a technique for dynamic load balancing where, rather than sort of this top-down approach of deciding what runs on which core when, we sort of make it the responsibility of the core, or some abstraction of the core, to say, I'm out of work, and I need to find something else to do. So it'll steal it from some other core in the system, for example. So this has gotten very popular lately. Intel's TBB, the Java and .NET concurrency libraries use this technique very heavily, and they have these really nice high-performance schedulers. Unfortunately, these are like big monoliths of code. It's kind of hard to take that and then add a GPU component to it, for example. So just to set the scene, what I would like to see us be able to do is take a merge sort program like this that uses the par monad primitives and is a reasonable implementation of a CPU parallel algorithm, and turned into something like this, where instead of just bottoming out to a sequential CPU routine, we spawn a computation that might actually wind up running on the GPU. Or if the GPU is completely full of work already, it'll go back to the CPU. Maybe it won't be quite as fast, but that work stealing is what's giving us this dynamic ability to maximize what's in front of us. So we have GPU in the sequential routine, but then distributed too in the recursive case, because we want to take advantage of all three at once. So Metapar makes that program possible. And what it is an extension of the par monad with a parameter that's a heterogeneous stack of resources. So this is essentially a representation at runtime of the various execution resources that you have in your system. These resources are composable, so you can take your ordinary CPU scheduler and then compose it with something that goes off and drives the GPU when necessary. And we don't have to commit to a particular choice of resource stack until runtime. We just make a new entry point by partially applying the resource that we want. So to give an idea of where we decided to place this abstraction, where we cut things off and leave things in the hands of clients and implementers, here's the regular par monad loop. We do a bunch of work on a local work queue. When that runs out, we look for work on another core. Well, so we spin if there's no work to be found on another core, but eventually we find some work to do, and the computation finishes. But instead of committing to that choice of looking for other cores, we have this parameterized stack that, in this case, is our CPU GPU distributed, but it might be whatever you want. So a resource, all you need to do to implement this resource is provide two functions. A startup function, which initializes the system, and a work search function, which gets invoked by any worker that has run out of work on its local queue. That's its source for more work. And these are all composable just with a simple binary operator. So a startup, to give you an idea of what you might have to write if you come up with a new architecture to write these schedulers for, just takes a representation of the state of the system. It's provided when the system starts up. And in the I/O monad, you can do whatever work you want. You can spark off new threads. You can initialize network connections to peers in the distributed setting. But we leave it to the implementer to decide what work they need to do in order to start and be part of our system. The work search takes that same group of global state and gets to decide on a case-by-case basis, called over and over again in this loop, here's some work for you to do. So compose startups just run in sequence. But work searches, we want this to be a stack. We want the SMP work to take priority over the distributed work because it costs a lot more to go distributed than it does to just grab some more work locally. So they're left biased. They just draw from the first source. And then the resources, you just compose the components and you have a composed resource. So the simplest example of a resource that I can think of that could actually get work done is a single-threaded resource. It just spawns one thread, and since it's only going to draw from its local work queue, the work search never returns anything interesting. What's more interesting is the work search for randomized work stealing on SMP machines. So this is a faithful re-implementation of the scheduler that comes with the par monad that you can download on Hackage. It uses the information provided to it in the callbacks to index and find the work queue of a randomly selected peer in the system, and it just tries to steal from that work queue. The GPU resource has a new spawn operator, actually. So we're not just forking CPU tasks, we're also forking GPU. And so we have to change the types around to hand back a future that will get filled in when the GPU computation finishes. So part of the issues with composability that we had were the system calls might block a thread and prevent it from doing useful work. So we used the approach of having a proxy thread for the GPU that avoids the blocking and communicates back to the metapar system through the work search. The distributed resource also adds a new spawn operator that just uses the Cloud Haskell remote procedure call techniques. And the startup initializes, does the handshaking with network peers, brings up MPI, however it is that you're communicating. And then the work search is an implementation of distributed work stealing. So as an example of how straightforward it is, once you have these individual resources, this is all the code that it takes to have a 3-level resource that has a full complement of SMP threads, drives a GPU, and also has distributed work stealing. So our performance numbers are preliminary, but they are encouraging. In the SMP plus GPU case, we benchmarked a merge sort of 2 to the 24 32-bit integers. And we found that we can get about 60% of the wall time of the CPU-only case when we use our dynamic backstealing implementation. For the SMP plus distributed case, we ran the embarrassingly parallel Euler-Toshinsong benchmark. And we found that our ability to combine SMP with distributed led to a pretty good initial advantage in absolute times over the HDPH library, which is an extension of the par monad with distributed capabilities. But as you can see, we kind of have some scaling issues, and as we increase the number of nodes, our performance goes down a bit. But this is a promising sign that it works this well to begin with. So there's a number of techniques that we draw on for this work. So most recently, the lightweight concurrency primitives for GHC uses a very similar architecture where a small kernel with a limited number of callback interfaces and primitive operations proves sufficient to implement some rather sophisticated performance operations. Live is a system that addresses the problem of resource contention when schedulers are composed by having a runtime notion of what a CPU is, for example, so that 2 instances of threading libraries don't compete for the same CPU. Manticore implements a number of CPU scheduling algorithms with, again, concurrency-based primitives. And as I mentioned, HDPH is fine work in the distributed setting. So, in conclusion, scheduler composition, particularly when dealing with multiple types of execution resources, is difficult. So we believe that work stealing is a good way to make things modular by reducing, as far as possible, the number of assumptions being made when you're composing the schedulers. And we think that our resource abstraction is a good one. It's served us well to implement at least these 3 sets of resources, but we'd love to see more approaches fit into our framework. And if you have any questions, I'll be happy to take them.